So once again, welcome to today's lecture. Today we are looking at optimization of transportation problem using a technique called modified distribution method. In our introduction to transportation problem, if you recall, we had introduced the concept of transportation problem, and we mentioned that this is just one special kind of linear programming technique that is concerned with the optimization of cost. It actually seeks to minimize the amount of cost required to transport some goods from some given sources to given destinations. And we even looked at the basic layout of a transportation problem, and that a transportation problem will typically have some sources on the left, then some destinations, so that this particular column will consist of the total supplies that the given sources can be able to supply. And down here, you shall have the total demands depending on the given number of destinations. And so this is basically what we did in the introduction to transportation problem. And so one key thing we emphasized under transportation problem, we say that transportation problem as a technique for you to solve a problem using this transportation problem approach, you have to go through phases. And the first phase was one we said that requires us to determine what we call the initial basic feasible solution. So this was like the first phase of solving a transportation problem. And we mentioned a number of techniques that we can actually use to obtain this particular solution. One of them was the northwest corner method. We had the least cost cell method. Then we finalized with the VAM method, or Vogel approximation method. And so this is basically what we explored in introduction to transportation problem. So in this lecture, we seek now to look at the second phase of this transportation problem, which now requires us now to carry out optimization of the very initial basic solution we have obtained at stage one. So how do we carry out optimization? And so it's good to understand how to get the initial basic before optimization. Now, just like in determination of initial basic solution has several methods, one of them being the northwest corner method, the least cost cell method, and the VAM. There are also a variety of methods used in optimization of a transportation problem. But today we are looking at one common one that we call the modified distribution method, simply just abbreviated as MODI in several literatures. You'll just find it as written as MODI method, or you'd see some books calling it UIVJ method. This is just, as we shall be seeing, shall be creating a lot of these variables, UI and VJ, they are called dual variables. So they are so unique with this technique that sometimes when you just call the UI-VJ method, it comes into mind, that's a transportation problem and optimization using modified distribution method. And so that is the scope of what we want to discuss today. And so under it, before we even dwell into it, by looking at the steps and the procedures one ought to follow in optimizing a transportation problem using this, we want to look at two concepts. One is how do we then check whether the basic initial feasible solution is generated. So that's the first concept that we need to know. And then the next one is drawing loops, because we shall be drawing several loops in this particular technique. So we want to look at these first few concepts first of all, so that once you have mastered how to draw a closed loop in the context of transportation problem, and then we shall be able to now go to the technique itself. And so then after that, after knowing that, we should then just be looking at the procedure. And I've just summarized these procedures into like 4 areas which have to be followed sequentially, where the first one will be checking the whether the basic feasible solution you have is non-degenerate or not. And then we shall be now be determining the dual variables, and we use the dual variables obtained to calculate what we call opportunity cost in this context. Then with the opportunity cost created, we can be able now to check for optimality test now, and we shall be knowing for MODI method, a solution is said to be optimal, of course, by fulfilling certain conditions, as we shall be exploring. And then if, of course, it's not yet optimal, then it requires us now to create some loops, which are kind of now iterations. So we begin, first of all, by looking at that introduction of looking at what non-degenerate basic feasible solution is before we proceed. So now that we know how to get a basic feasible solution using the 3 mentioned technique, the least cost cell method and northwest corner. So that basic feasible solution will only be said to be non-degenerate if it contains exactly m plus n minus 1 allocations in independent positions. Now, what m and n here stands for is that if I have a transportation table like the one displayed, then m will be standing for the number of rows. M will be representing the number of rows. So like in this case, there are 3 rows. So here m is 3. Then n will be representing the number of columns. So n is actually 3. So these are transportation table of, let's say, 3 by 3, where you're talking of m rows. The rows are 3 and the columns are 3. And so once you have it, you always want to find out how many cells have received allocation. Because these are 9 cells, but the ones that have received allocation or have been assigned some units is this particular cell 1, 1, cell 1, 3, cell 2, 2, cell 3, 2, and cell 3, 3. So the ones that have received allocations or the number of assignments or allocations is actually 5. So those are the number of allocations, 5, and they are all in independent positions. And then now you check. If I sum the number of rows and columns, m plus n actually gives me 6, because you're talking of 3 rows and 3 columns. So that means m plus n minus 1 will actually be 5. And this 5 is also equal to the number of what? Of cells that have received the allocations. So in this particular case, we shall say that this basic feasible solution, and you can see the allocation of this, this basic feasible solution will be said to be non-degenerate. And the condition for testing that is just checking whether the sum of rows and columns less 1 is actually equal to the number of cells that have received allocation in that particular transportation table. So for this particular one, we shall say the basic solution is non-degenerate. So in the event that we don't have that equality holding, where we don't have m plus n minus 1 equal to the number of cells allocated, then in the event that this equality doesn't hold, then that is when we say that the solution is degenerate. And so For us to solve a transportation problem, we shall always be seeking to work with non-degenerate basic feasible solutions. And so in the event that the solution you have is not a non-degenerate one, then some adjustments will have to be taken so that we convert it into non-degenerate before we are able now to adopt the techniques of solving the transportation problem that are laid down in this literature. So, but that would be on a rare scenario to encounter such. So that's one concept that we need to understand. Then the second concept that I also want us to understand before we narrow down to looking at the procedure for Modi method. Yes. Sorry?
Oh, back to the table, Mali.
Yes.
Okay, I just want to ask.
Yes.
How you allocated those is it the columns or those boxes? Or the question comes like that?
Now, for this particular case, you know, when you have done I've assumed in this particular case, maybe you have used say the least cost cell method, or you have used the northwest corner method, and you're getting the final table like this before you now calculate 8 times 37 times 10, 3 times 25, 5 times 5, you get. So I've just picked one with allocations. So, but we are going to demonstrate one where we shall require to begin from location using the methods we learned before we now do the optimization. So that should not worry you. Here we are just saying, suppose you have a table and you have such kind of allocations. If you look at the number of allocations, the cells that have been allocated, and the sum of rows and columns less one, do they tally? So that's basically what we are just looking at this particular point. Thank you. Hope that's okay. Now, identifying as we are saying drawing closed loops is another concept that comes in handy whenever we are using modified distribution method. And one will wonder, a loop, when you're talking about a closed loop, a loop is just a path. But the path that we are going to be drawing in this context, of course, if it's a loop or a path, there must be a starting point. There must be a starting point identified. And so, but in this context, the identified part of point will actually be an allocated cell, a cell which eventually has not received any units assigned to it. Will actually be our unallocated, our starting point. That's where we shall be drawing our loop starting from. And then our loop will only be consisting of horizontal lines and vertical lines. At no given point are we going to draw maybe diagonal lines or wavy-like lines. They are going to be only horizontal and vertical lines. And then these vertical horizontal lines, from that starting point, they'll be moving towards a cell which has received some units allocated. Remember, we are beginning with a cell that is unallocated, and we are moving either horizontal or vertically to another cell which has some units allocated to it. And then another thing is that it can only be a loop, of course, if we are going to make some turns. But the turns here, we are emphasizing that the turns must only be 90 degrees, that only turns at right angle are allowed. And these turns, you only turn towards a direction where there is a cell with some units allocated to it. You don't turn to a direction towards a cell which has no units. And of course, and then we're also saying that the loop must be closed, and therefore you must come back to the starting point. You must come back to the starting point. So from this, you realize that you may have a loop of this nature, just a square, because you're making only turns at 90. And that can be a loop. As long as if this is your first cell, this is an allocated, but this one has allocation of units. This one has units allocated to it. This has units allocated to it. This will be a closed loop. A closed loop will also be taking maybe this kind of, it can even take such kind of thing. It can be even this way. This can also be a loop. As long as, if this is a starting point, you have no units allocated at that particular point, but there are units allocated in this cell. There is allocation of units in this cell. There is allocation. There is allocation, and you can see we are moving horizontal and vertical. And anytime we make a turn, it's at 90 degrees. So if I'm following this route, it's horizontal and I'm making a turn of 90, and I'm making a turn towards a direction of a cell with units, then I'm making another turn, This can also be complete loop. So loops can be rectangular, can of these shapes are several, and so on. In fact, I want us to use the first table that we have just drawn to see whether we can be able to draw a loop. So I have this particular table. So we want to make use of the first table that we have drawn, this table, which has, you can assign the allocations. You can assign this first cell the way it is. Just assign them the way they are. We shall see how they are obtained much later. But just assign those units the way they are so that we see how we can be able to draw a closed loop. And we are saying in this case, all our closed loops will begin, the starting point will be a cell with no units allocated to it. In this particular case, you can see this cell has no units allocated to it. This one has no units allocated to it. This one has no units allocated to it. And the other cell also has no units allocated to it. So there are 4 cells with no units allocated to them. So they are called unallocated or unoccupied cells. But we want to draw a closed loop starting with now cell 3,1. So specifically, we want this to be our starting point and draw a closed loop. Maybe you try to draw from your end, or maybe draw this one together, and then the second one, example, I can allow you to. So from here, we either move horizontally or vertical to a direction where there are units allocated to it. In this case, if I move upwards, it's okay because there is again a cell allocated in this cell, so it's still okay. I can also move towards the right, horizontally like this, because there's also units allocated to it. So I'll move straight to that particular point, but one may ask, why am I skipping this first cell? But I'm going to answer that shortly. So if I move like this to this cell, I can still have a turn of 90 degrees this way. Then I still can make a turn to another cell with units allocated to it. So that is then I need to make a complete loop by coming back to the starting point. So this way will be, you may draw the arrows or you don't need to draw the arrows. The way is good. So that's a closed loop starting from that particular point, 3,1. And so to answer the question, I was just saying that why didn't we just stop at let's say, if I was moving this direction, why didn't you just stop at this particular point and move to this direction? Because it also has some units. Yes, it's okay to move up to this particular cell, but the only problem is after getting here, you can't go to this one because this one has no units, so you not turn. Neither can you go this direction because this one also has no units, so you not give you a chance to turn. You can't come this way because this one has no units assigned to it, so you cannot give you a chance to turn. And therefore, you'll end up failing to make a complete loop. You'll end up failing to make a complete loop. And so the only choice you had, just hold on, the only choice you had was to move straight to this particular cell, then back, and then that way. Yes? A question?
Yes, a question.
Yes.
You said we can't move to 4, 5, 9 because they are unallocated. But we started from 8, which is also unallocated.
Maybe I go back to the procedure I've just mentioned because I've said for you to draw a loop, the starting point must be unallocated, but the rest, you only move to direction which is allocated. If you look at my procedure, that the starting point must be an allocated cell. But from there, you only draw lines horizontal or vertically towards allocated cells.
Okay.
I think that answers the question, right?
Yes, Mali.
All right. Any other question as we proceed? Thank you. Silence means we are okay. We can try this second one now. The second example, I want us also to draw a closed loop. But this one now, the starting cell I've mentioned, let's pick 2, 1, because it also has no units, this one. And let's see how we draw a closed loop. So let me give you a chance, 1 minute to draw the loop. Now that you have your second, you can use your second table. You can, because you have drawn the table, you can just assign those units and draw it. Have we drawn the loop? Have we drawn the loop?
Yes.
Thank you. So here you have choices. You can either go this way, or you can even go upwards, because the 2 directions have units assigned to them. So if I choose this, I'll come to that cell 22, and that cell 22 give me a chance to turn. I cannot go horizontally all the way to cell 3. So I can only come down to cell 32, which also has some allocation, and make a turn of 90. Then I can also make that horizontal now, move to that cell 33, and I can make a straight vertical one all the way to this particular cell which has allocation. Then from here again, I make all the way the other one which has allocation, and I'm able to turn now to the starting point. And I'll be able to have made a complete loop by making movements that are only horizontal or vertical, starting from a cell with no units allocated to it. And that's the cell that we've been instructed to draw the closed loop. Is it better now?
Yes.
Is it better?
Let's clear.
Yes, Mali.
Yeah, maybe one last one. I don't have a slide for this, but let me just change this to cell. Let's say I'm seeing cell 2, 3. This particular cell, I'll draw mine with a red pen because I don't have a table for it. Maybe for you may want to use another table to do that. So if we begin from this particular cell and we want to draw a closed loop, how will it appear? Let me just sketch that. So you'll allow me now delete the blue one. And let's draw a closed loop. Are we done? Now for this particular cell now, if you have to draw a closed loop, what will happen is that, yes, I can move to maybe upwards, horizontal or vertical like that. And I can still move horizontally like that, vertical. And even this one, because it has units, gives me a chance to make a turn, but I'll not be able to make a turn to come to the starting point because these two cells have no units allocated to them. And so that going that route therefore becomes forbidden because you'll not be able to make a complete loop. And so now you are left to either going horizontally or vertical. You can now maybe move horizontally like this. And you come to this cell with units. Then from here, you can make a turn towards another cell with units allocated to it. You can still come this way because it has units, and you can now make a complete turn like that. And so your loop will be rectangular or square, depending on how you look at that. So that is a closed loop, maybe starting with the cell 2, 3 in this case. Are we now okay with drawing closed loops from a cell that has no units allocated to it? So that we move on.
Okay, Mwalimu.
Thank you. Your response is key. Otherwise, I'll interpret we are doing well. Now let's now go ahead now and, and get deeper into MODI method itself. Now that we have known how to check for non-degeneracy of a basic feasible solution, and we have known how to draw closed loops. Now the procedure for optimization using MODI, we require that first step, you check for non-degeneracy, what we have just been doing. You check whether the sum of rows and columns less 1 is equal to the number of allocated cells, and you desire that this becomes true. But if that is not yet, you don't get that scenario, then you don't go now, you go to, even though we are saying you go to step 2, where you'll be now dealing with the conversion of now some unallocated cells into allocated so that this particular property can be fulfilled. Now in this lecture, we don't want to be now dwelling on how, on the response now, and what to do with the conversions. So we shall be looking at, yes, Vincent.
How did you allocate those cells?
How come today the voice is so low? I can't hear you people clearly. I've tried to maximize the volume from my end. Hello?
Yes, Mwalimu.
Hello? Yes.
Hello, can you hear me?
Yes.
I'm just asking, how did you allocate those cells?
The cells I've just allocated randomly.
Okay.
The concept is not at that particular point to let you know how to do the allocation, but it's just random. I'll give you a real example so that you allocate and then you do the rest. Huh? My concern was just to show you how to do the loop and how to test for non-degeneracy.
Okay.
Yeah. It was not to teach you how to do the allocation. Huh? All right. Thank you. So we now look at how to convert, the second step we have said converting the necessary adjustments. That is if condition 1, that's step 1, this condition doesn't hold. But as I've said that most of our problems, this condition will be holding. And so if this condition holds, you'll be going straight to step 3. So from step 1, after checking this, you'll be coming to step 3, where you'll be now be determining what you call dual variables. And these are variables that are basically denoted by UI and VJs, the UIs and VJs. So in this case, what we'll be doing is that you'll be using this condition ui plus vj is equal cij, where, so the ui and vj are the ones I'm calling the dual variables, and cij, remember, we introduced cij now in the introduction to our transportation problem, where we said cij stands for the costs. So this will be now maybe the cost of our unit, maybe in cell Cij, yeah, the cost in cell Cij. We are talking of if our row is labeled I in a particular column J, then the cost of maybe transporting a single unit of product, maybe from source I to destination J. So what we are calling Cij. Then using the computed UI and VJs, we shall be calculating what we call the opportunity cost, which will be given now by this. Just like getting this sum, subtracting this from that, we are going to see, but now this opportunity cost, we shall be using unallocated cells to calculate the cells that have not gotten the chance to be allocated. And then our interest, when we calculate the opportunity cost, will not be the magnitude, but the interest will be the sign, whether the opportunity cost obtained is a positive value or a negative value. And so we desire that we get a positive value. So we get a positive value of opportunity cost for all the cells that are unallocated. Then for us, we shall be quick to report that the solution has actually reached its optimal point. But in the event that we get one of these unallocated cells giving us a value that is a value of the opportunity cost that is negative, then that will be giving us room to actually spend less in terms of the cost of transporting those goods from sources to destinations. So it will be telling us that the solution we have at hand is not the optimal, but we can further minimize the cost. And then now, so if it gives us room to further minimize the cost, then we shall be getting to a stage now where we shall be now beginning to draw loops, and these are closed loops. And in this case, we shall be looking at among the cells that are unoccupied, we look at the cell that is unoccupied with the smallest negative opportunity cost, and then treat that as the cell that we now seek to assign some units. And so we draw a closed loop from that cell. Then once you have drawn this loop, you can see when you have been drawing loops, we are getting corners. So if we have drawn a loop and it appears like this, and this loop we have drawn starting from this point, we begin assigning now alternate positive and negative signs, starting from the cell that you have begun. The starting point of the loop, you assign positive, then alternatively, you assign those signs. So if this is positive, this is negative, this is positive, this is negative. So that's how we shall be assigning those signs alternatively from the starting point. And then once we have done that, then we now determine the number of units that should be now shipped to that cell, that starting cell, because it was unoccupied, so that we want to assign it. And then for our interest, we shall only be checking the corners marked with minus sign and see which one has the lowest amount of units assigned to it. So that lowest amount of units assigned to it will be the amount that we shall be shipping to this cell and allocated at the starting point. And then we shall be doing now the readjustment of the entire transportation design. Maybe through an example, we can be able to demonstrate this better so that our members can be able to understand. So I hope we have another table. We draw this table again, but you have drawn several of them. So I want us now to begin given a transportation table of this format, so that we begin from the first phase where you are determining an initial basic feasible solution. Then from that first phase, now we go to the second phase where we need to do optimization using MODI method and see how we can now apply the steps that we have just highlighted. So maybe you begin now. In this case, I want us to use the least cost cell method so that we all end up with a uniform solution. as the basic initial solution. Then we do the optimization. So maybe 3 minutes now that we know how to find the basic initial feasible solution. Let's use the least cost cell method to determine the basic feasible solution for this kind of transportation problem. Are we through? Hello? Maybe we do it together just to help those who have forgotten what we are doing. So the least cost cell method requires us to identify the cell with the least cost in the entire transportation table. So in this case, this is a cell with the least cost and the cost is 3. And so we assign it first. So when you compare the row total 25 and the column total 30, so we shall assign 25 to this particular cell, 25 units. And in so doing, we shall then have depleted what source 2 can be able to supply, and therefore no destination again will receive any other units from source 2. Then from here now, but then destination 2 will still be having a demand of 5 more units to meet its requirement. Then now when you look, consider the remaining cells with 8, 9, 7, 8, 5, 6, you realize that 5 is now the least cost. And so we compare 5 and 35. So we assign 5 here so that we are able to meet now the demand of destination 2. But then we shall still be having 30 more units that source 3 can be able to supply. Then again, we check between 6, 7, 8, 8. At the lowest cost is 6. So we assign this first, and this one you're going to assign 30 so that we are able to meet to exhaust source 3, and then but then destination 3 would still be requiring 10 more units to meet its demand. Then of course now again the remaining cells, this will be the least cost. So 10 and 40, we assign 10 here. And therefore that way we shall have met the demand of destination 3. But source 1 will still be now remaining with 30 more units that can be supplied elsewhere. And so the remaining cell now, which is this, comparing 30, 30, it will just have to receive now the 30 units from source 1. And so this now becomes the final allocation. And so we do 8 times 30, 3 times 25, 7 times 10, 6 times 30, 5 times 5 to get the initial basic solution for this problem. And so this is what we have just done, and you have obtained that. And so when you do the multiplication, I'm sure all of us are getting this figure. So just confirm that you have gotten that figure from your end, at least from a few of us. Hello?
Yeah.
We are getting the same figure?
Yes, Molly.
Thank you, thank you, thank you. Now that is what we did last time, and that's what we're
Yes, yes.
And so those who have been asking how those allocations have come, I told you to assign them randomly. Now you see how that is. Huh? Now, part B now, using modified method, determine the optimal solution that minimizes the cost of transport. So in other words, what that 590 says is that roughly we can spend 590 shillings to transport all those goods from their sources to their destinations, the 3 destinations, from the 3 sources to the 3 destinations. This is the amount, what that first step tells us that we can spend. Yes, we can spend if we have, but you see, if you are in business and if you are doing optimization, you want to see whether you can save some more amount of money. So you want to see whether you can spend less than 590, but still meet the demands of all the destinations and exhaust all the supplies from the sources. So that is what now optimization now comes in. And that's where MODI method comes in as far as transportation problem is concerned. We want to see, is this the minimum possible amount you can actually spend in transporting goods from their sources to destinations, or you can spend a little bit less. And so that is what we are doing. And so if we can spend a little bit less, then that would be better for us. I know those who are not in the class of introduction to transportation problem are asking whether this is true. Please find time and go through the slides, the recording for introduction to transportation problem. It will do you a good deal. But what we are doing here is that to get the 590 is simply just getting the product of this 8 times 30 plus 7 times 10 plus 3 times 25 plus 5 times 5 plus 6 times 30. That's what we are doing to get the 590. Now, optimization, now the MODI. Now, MODI method now, we said once you have determined, we now need to check, because I've now extracted those cells that we have just multiplied 8 times 30. The ones that have received allocation are the ones I've just isolated now, so that the table is a bit cleaner compared to the rest. So you do the same from your end. Just have a table that is clean with now with the allocated cells the way we have obtained in that query, so that it doesn't appear dirty a bit. So that now we can begin now determining the dual variables. That's this dual variables. you can see the condition of non-degeneracy here already holds, because there are 3 rows, 3 columns. So those are 6 less 1 is equals the number of cells allocated 1, 2, 3, 4, 5. And C6 minus 1 is equals to 5. So that condition still holds. So we calculate now for the dual variables, the UIs and VJs. So I always label the rows as U1, U2, U3. So those are the UIs. So that U1 is the first dual variable for one, U2, U3. And then I label the columns as V1, V2, V3. So you can also label them the way I've labeled, because we now want to find their values. We want to see what's the value of U1, what's the value of U2, what's the value of U3, and what's the value of V1, what's the value of V2, what's the value of V3. If you have assigned, you alert me so that we go ahead. There's a table you have already drawn. Can we proceed?
We proceed well.
Thank you. Now, the condition that we are only going to use here when solving and finding the values of these dual variables is just this condition we are emphasizing, that UI plus VJ is equals to CIJ. In other words, if I'm talking of V1, U1 plus V1 should be equal to C11. And remember, C11 here is 8. C12 here is 9. C13 here is 7. C21 here is 4. C22 here is 3. C23 here is 5. C31 is 8. C32 is 5. C33 is 6. And you're having the U1 ones. So in other words, if I'm talking of this U1 plus this V1 should give me this C11. This U1 plus this V2 should give me C12. This U1 plus V3 should give me C13. This U3 plus V1 should give me C31. This U3 plus V2 should give me C32. This U3 plus V3 should give me C33, and so on. And that's the condition we are using. And so you are seeing like there are a set of linear equations if you are to write all of them. And so to solve them simultaneously, what happens now here, and simultaneous doesn't necessarily mean 2 equations. Here there are several. Actually, you can find this combination. There are about 9 equations you can write. Because this one I've only written 1. U1 plus V1 is equal to C12. U1 plus V2 is equal to C12. U1 plus V3 is equal to C13. So there are several, all those sets of equations. And so for you to solve them, you need to fix at least one value of the U's or one value of the V's. You need to fix it. Assign it a particular figure. Assign it a particular figure. I like using 0 because 0 is easier sometimes to substitute and to minimize on the errors you are likely to make. And so if I assign and say and you can let any, whether V1 or whether U1 or whether U2 or whether V2, you can assign any figure, let's say a 2 or a 1 or a 3, even a 10 or a 20. But assigning a bigger number, you give yourself challenges of computation. So you rather just assign a small figure. For example, let's suppose I assign U1 as 0. But let U1 to be 0 so that I can now be able to get, if U1 is 0, what is U2, what will be U3, what will be V1, what will be V2, what will be V3. Now, if I've assigned U1 a particular, a given figure or constant like I've done, for me to get the rest of the dual variables, I've given you a hint here. And the hint here is that use only the cells that have units allocated. Only the allocated cells will help you now be able to determine the rest of the dual variables. Now, we have said like U1 plus V1 should give us C11. That's what you have agreed. That this U1 plus V1 should actually give us C11, which is 8. So that means if I've fixed U1 to be 0, and I'm saying this 0 plus V1 must give me C11, which is 8. So what do you think will be the value of V1? What do you think will be the value of V1? Hello, we need to communicate, guys. So V1 would be 8. Thank you. Thank you. Why I've used this is because this cell has allocation. So I've gotten now to know U1, I've gotten to know V1. Then this cell also has allocation. And you can see I can create an equation there and say U1 plus V3 should give me 7. Should give me 7. Now, if U1 plus V3 should give me 7, U1 is 0. Then plus V3 should be 7. So that means V3 is going to be 7 as well.
7.
Right? Thank you.
Yes.
So V3 is also going to be 7.
7.
We are doing great. Now, you ask yourself now, this cell also has some allocation, huh? And I can create an equation for this because I have a U3. I know that U3 plus V3, isn't it? This one plus this should give me 6, huh? Should give me 6. The C33. But you know V3 now, because you have known if V3 is what? 7. But you don't know U3. But this gives you 6. So what is U3? What would be the value of U3? U3 is going to be?
-1.
-1, correct. So you now have U3 as -1. We are doing well. We are only remaining with U2 and V2. But take in mind, you can see I'm only walking around to check only the cells that have units allocated to them so that I can move to this particular cell because at least I know U3 and I don't know V2. I can be able to get the rest. So let's see. You know that U3 plus V2 is actually equal to 5, huh? But U3 I've said is -1 plus V2 you don't know. This should actually be 5. So what is V2? What is V2?
6.
Thank you. This is 6. So V2 is 6. You write that V2 equals to 6. And we now have only one dual variable. And that is U2. But if I use this particular cell, now that I know V2, because U2 plus V2 now should give me a 3. That means I can still get it as well. And so I can say that U2 plus V2 should actually be equal to 3. So that means U2 plus V2, which is 6, should be equal to 3. So what is U2?
-3.
-3. Good. So we have calculated our dual variables. That's our second step in optimization using MODI method. You calculate the dual variables. And for you to do that, you are assigning the dual variables on the columns and the rows, U1, U2, U3, V1, V2, V3. And what happens here is that because there's several sets of simultaneous equations that need to be solved, it's good for you to fix one of the U's, one of the V's. Now, if somebody fixes U1 to be 2, the corresponding values of U2, U3, V1, V2, V3 will not be the same as what you have obtained, but that should not worry you. Eventually, when you'll be optimizing and calculating the opportunity cost, they will still give you the same results. They still give you the same results. So it's not like cast on a stone that U1 must always be 0. You can even begin with U2 fixing it to be 0. Maybe the next example we shall assign something else, a 0 or a different figure altogether. Now, once you have done the dual variables, we need to calculate what we call the opportunity cost. And the opportunity cost, like I was emphasizing on the procedure, the opportunity cost, we use now the cells that have not received the units at all. The cells that have not gotten the chance to be allocated any units. As you can see from here, the cells that have not received any units allocation, we have this particular cell, this cell 2.1, no allocation. This cell 3.1, no allocation. This cell 1.2, no units allocated to it. This cell 2.3, no units allocated to it. So those are 4 cells that have not received any units allocated to them. And so those are the cells that we are going to use to compute what we are calling the opportunity cost associated with each one of them. And so I'll want us now to sketch a table of this kind so that then we are able to calculate for each. So you see, I've created a table. So we are testing now for optimality, but before that, we create a table. So this is a table of cells that have not received any units. So cell 1, 2, cell 2, 1, cell 2, 3, and cell 3, 1. And the other column is opportunity cost. So we want to calculate these figures and see what they give us. Because I had given you the formula for calculating these figures. I'd given the formula for calculating these figures. I said Cij minus the sum of those corresponding dual variables. So let's draw first before we go back. I suppose you are done. You may not really struggle to write these formulas. You can as well just omit them. There's no harm. These ones you may as well just omit them. But because once you have written the other one here, I just wrote them just to help someone who is not seeing maybe how we are getting them. But they are really, really, really not a must. It really is really not a must for you to write them. I really need a figure. So let's begin the first cell, cell 1, 2. Cell 1, 2. So the cell that, the first cell on the first row. So we are looking at this cell with this particular cost 9. So to find the opportunity cost, we are talking of 9 minus the sum of 0 plus 6, because U1 is 0, V2 is 6. So 0 plus 6 is 6. 6 subtracted from 9 gives us 3. You see that? 9 minus, it is C1, 1, 2 minus U1 plus V2. This plus this subtracted from 9. So 9 minus 0 plus 6. So that gives us 3. So 3 is the opportunity cost associated with that cell that has no allocation. So 3 becomes the figure that we write there. Then we look at the second cell that has no allocation, cell 2-1. Cell 2-1 is actually this particular cell, where we are now talking of C21 should be now equal to U2 plus V1. So you're talking of -3 plus 8. You're subtracting from 4. -3 plus 8. You agree with me that -3 plus 8 is actually 5. So that 4 minus 5 is now going to be -1. Do you see that?
Yes.
Hello?
Yes, Mari.
So this is going to be -1 as our opportunity cost associated with this. So let's calculate the opportunity cost for the remaining 2 cells. Let's calculate the opportunity cost for the remaining 2 cells. Are we done? So what are we getting for cell 2-3? What's the opportunity cost? Hello?
One.
You're getting
One,
1-1 for the 2.
Yeah, thank you.
Yes.
It's 1-1. That's correct. That's correct. Now, it is upon getting this table that we can now be able to tell whether the 590 figure we got during as our basic initial feasible solution is actually optimal. So we have calculated the opportunity cost associated with that particular associated with the unallocated cells. So the test will only be said to be optimal if all these values, the test will only be said to be optimal if all these values are positive, 0 or a positive number. But the moment we get at least one of the cells that is unoccupied giving us a negative figure, then it means that the amount you have gotten as the total amount at the level of basic initial feasible solution. Remember, like in this example, we have 590. So when you get a figure like this being negative, then it means there is at least a possibility that we can spend slightly less than this to transport goods from their sources to destinations. And so it gives us a chance to now seek to find what is this small amount we can spend so that we save a few coins instead of spending 590 to transport the goods. And so we begin with now with that cell that has given us a negative figure. Now the negative figure here, the cell corresponding to it is this particular cell 2-1, which is giving us a negative opportunity cost associated with it. Now we go for it now. And that's why you can see I've written some comment there that since the negative values of opportunity cost, this solution is not optimal. The total cost can be reduced further. So I want us to have a clean table of that kind. And before we now begin creating the loop, we need to begin creating the loop from this cell 2-1 that has given us an opportunity cost of -1 as the only cell that gave us a negative value opportunity cost. So that is the cell that we are more interested in. That is the cell that we are more interested in. So this is a cell. So that means this cell is unoccupied, has no units. So we are going to draw the loop from this cell, a closed loop from this cell. Now that we have known how to draw closed loop, I suggest that we now go ahead and draw a closed loop for that. A closed loop starting from that cell 2-1. Let's draw the closed loop. You're done? This appears we had already done this because we say we are only drawing horizontal and vertical lines. And they should be
Yes.
vertical. So this is going to be our loop. Only making turns in the cells where there is allocation of units. Now, after drawing the loop, the next thing we need to do is to assign negative and positive sides to the corners that we have marked, the corners where we are making turns. But we begin the starting point, assign positive. Is this issue an issue of internet? Can you still see my screen?
No.
No, Maria.
Sharing. No.
I need to
No.
share. It's okay, it's okay. Suppose it's okay now.
Yes, we can see now.
Thank you. So we had drawn the loop and we were just assigning the corners of the loop with alternating plus and minus signs before the internet messed us up. So we are saying the starting cell must be positive. So this one will be negative, this one will be positive, and this one will be negative. So you have assigned the loop, making sure that the turns have alternate plus and minus sign, but the starting cell must always be positive. Now, once you have assigned like that, our interest now is to look at cells with negative sign. Cells with negative sign. Remember, this loop has only one cell which is not allocated units, and that's the starting cell. And that's the cell that we want to assign some units so that probably now it doesn't fall in that category of unallocated cells that have opportunity cost giving us negative values. So for us to look at that, so you can see that cells with the only cells with the negative sign are these particular cells. This one. These are the only cells with negative sign in this case. And when you look at those cells, this first one has 30 units allocated to it. This second one has 25 units allocated to it. This third one has 30 units allocated to it. So you compare 30 and 25, those figures. The lowest figure is 25. Because the lowest figure is 25, it means that 25, those are the units we are going to ship into this cell. So 25 now going to be awarded to this particular cell. 25. We are going to move them from here. So that this is now going to be a cell now that is eventually now going to lack units. So it's going to be one of the cells that is now unallocated. Now, when we ship the 25 to this particular cell, because this cell has a positive sign, any other cell that has a positive sign in those corners, we also award it 25. We awarded the figure that we have ferried or shipped. So like these cells and the cells with the positive sign, if I may highlight them, we all can see cells with the positive sign are like this particular cell. Sorry. Cells with positive sign are this cell, this one, actually those ones plus the starting point itself. So those cells must be added the 25 units. So that means this one now from 20 plus 25 is going to be 30. And this one now, because it's 10 plus 25 is going to be 35. It's going to be 35. Now you'll ask now, what happens to the other cells with the negative sign, apart from the cell we had shipped from? So what happens is that now the other cells which had negative sign, like this 30, where there is negative, now you minus 30 minus 25. You remain here now with 5. And you remain here with 5 as well. Why we are doing this is just to make sure that the row totals and column totals are not affected. You can see that destination 1, when you have 5 plus 25, you still get 30. Destination 2, you only have 30 in this last cell of 32. And destination 3, 35 plus 5 gives you 40. And even if you check row-wise, row 1, you are talking of 5 plus 35, which still gives you 40. Row 2 is 25 plus 5. Row 2 is what? Has it changed? No, this is not 5. 5 is the cost. So row 2 is still 25, and row 3 is still 30 plus 5, 35. So where the cells with positive sign, we are adding that amount that we have shipped, and the remaining cells of the negative, we are actually minusing the figure we have shipped from them. So that now the new transportation table will actually appear as shown after doing the shipping. This is the one which had units. We have now shipped its units to the other one. And this one we added, this one we added. Now this one we minus, they are now appearing like that. So this is now a new kind of allocation done. Not through now the means of least cost cell method, neither through the least cost cell method or the VAM method. Are we fine up to there?
No, Mwalimu.
No, Maureen.
Ask Mwalimu, come up again.
That's fine.
Adding and subtracting 25, I can't get it.
I thought that is the easiest maths, you know. Yeah. Let's come again. There's no harm. Let's delete these things, so that people can also draw. But drawing the loop, we had no problem, right?
Yes.
Mwalimu. With the loop, we are okay.
The loop, we are okay.
Yes.
That was the loop. Now, after drawing the loop, we said we now assign alternate signs, positive and negative. Starting with the starting point of the loop, that cell that is on the loop, that is the only one with no units allocated to it, is the one that is getting a positive sign first, right? Then we do alternate. So if this is positive, the other corner will be negative, this corner will be positive, this corner will be negative, this corner will be positive, this corner will be negative. We are fine up to that stage? Hello?
Yes, we are fine.
That's
Yes.
fine. Now, from there, we said now that for us, we are only interested with those cells with negative sign. Ideally, we want to award this unallocated cell some units. And when you look at this technique, is like we are going to snatch the units we are assigning it from one of the cells that are actually on the loop, those corners, so that we award it. And so particularly now on the corners, you're only checking the cells with negative. Only one of the cells with negative will have its units lost. And you are checking now, I said when you look at now cells with negative sign is only those three. So check the units allocated to those particular cells and pick the list. So it happens that this cell has 30, the last one also 30, and this 25. So among the three, the lowest is 25. So it is that 25 figure that we are now going to move to this particular cell. So that this one will now be 25 and this one will be nil, as no units now. But because this has a positive sign and has been allocated 25, it means any other cell with a positive sign should also receive more 25. That's why we added 25 to this particular cell to be 30, to move from 25. We added this was 10, we added 25 to be 35. And those are the only cells with a positive sign. Now, those with positive appear to be receiving additions. Now, those with negative now should be losing 25, an equal amount that their counterpart with the negative has lost. So they should also lose. So the 30 here, which has negative, will lose 25 to remain with 5. The third here will also lose 25 to remain with 5. So that now the new design with the new allocations will now have this cell allocation, this cell allocated, this cell allocated, these two allocated. But this one in the middle now will now be lost. It will now fall in the category of cells with an allocated, with an allocation or unoccupied. So that now the new design appear in this way. Is it better now?
Yes, Maureen.
That's better.
Thank you. Now this is now the new design. Now we need to check what is now the basic solution. When you work out here, what is the total cost when you do the product here? Is it still 590 or lower? We expect it to be lower. Let's do the costing here. If we are talking of 5 times 8 or 8 times 5, 35 times 7, 25 times 4. Then we are talking of 30 times 5. Then we are talking of 6 times 5. What are we getting here if these are shillings? What are you getting?
565.
5?
65.
Yes, so that means you can still spend 565 to transport all the goods from the 3 sources to the 3 destinations, meeting their demands with the 565 if you do this kind of allocation that we have. Now, but this is an iteration process. You don't want to stop here. You want to check whether 565 is actually the most optimal or the least amount possible. You want just to be sure. Can I reduce this further? Is there a way I can spend slightly less than this and still ferry all the goods from their sources and meet the demands of the destinations? So you need to check whether this new design or new allocation is still optimal. And for you to do the test of optimality for this again, you check, of course, you begin by checking the non-degeneracy condition. The number of allocations are still 5. And the sum of rows and columns less 1 is still 5. So that condition is still holding. Now you need to begin again creating a new set of dual variables. A new set of dual variables. So you can now begin again labeling V1, V2, V3, and then U1, U2, U3. Let's begin. You have gotten 565, that's correct. Now let's begin creating now that set. The new set of dual variables, just to check whether 565 is actually the most optimal. So in this case, which one do you want us to assign? Is it U1, U2, U3, V1, V2, V3? Which one do you want us to assign first? Let's pick one out of all these.
U1, V2.
We want to assign which one first? You know, we the other one, the other iteration, we picked U1, that we assign U1 first. Do you have preference so that it doesn't appear like I'm the one who's choosing what to begin with?
U2, V2.
We begin with
U2, V2.
U2. So U2, we assign it what? What do you assign it?
What are you doing?
Let's assign it a figure. U1 the other time we assign a 0. We can assign it any figure, even 1 or 2. Yeah? It's not bad.
Use 0.
You can assign 0.
0.
Yes.
Okay, so let's assign U2 0. Let's assign U2 0. And that is not from me. Huh? So let's begin now. We are using cells that have allocations. We can begin with this, because you know that U2 plus V1 should give us what? 4. Do you see that? U2 plus V1 should give us 4. Do we see that, all of us?
Yes.
So let's find V1. Let's find V1. Let's find V1. V1 is what?
V1 is 4.
4.
V1 is 4, correct. Aha. In that row 2, there is no another cell allocated, so it may not help us to get any other. We can come to row 1. Row 1, I think we can get U1. Because in row 1, you are seeing U1 plus V1 should give us what? 8,
8.
right? So
Yes.
let's find U1, because you know V1 now. Let's find U1. Let's find U1.
That is 4.
It is still 4,
Mm,
because you have said this is 4. So U1 plus that. So this is giving us 4. That's correct. Good. We can come here and get V3, yeah? Because we can see that U1 plus V3 is actually equal to 7. U1 plus V3 is actually equal to 7. So let's see if we can find V3.
3.
All of us anonymously see that. 3, yeah? Thank you. Now, with that, I think we can now get even U3. Because you can see that U3 plus V3 is equal to 6. U3 plus V3 equal to 6. You know V3. So what is U3?
It's 3.
3.
3.
Yes.
Thank you. And we can now use this as allocation. You know that U3 plus V2 equals to 5. So what is V2? What is V2?
2.
Yes?
2.
2. That's correct. I hope all of us are getting these figures. Now we now go ahead and calculate now the opportunity cost associated with cells that have no allocation. And the first cell will be this particular cell 1, 2. Then we shall have this cell 2, 2. We shall also have this cell 2, 3. We shall also have this cell 3, 2. With the dual variables we have obtained, we calculate that. And so we create a table of opportunity costs like we had created before. I've extracted those cells that I've just mentioned. And so we want to calculate the opportunity cost. So let's go ahead and calculate the opportunity cost associated with that and fill in. Are we through? The first cell, what are we getting as opportunity cost?
3.
3, that's correct. The second one?
1.
That is 2, 3, yeah?
Yeah, which is 1.
Quiet, let's see. We say 2, 3 is which one? This one, huh? This is 2, 3. Oh, the second one is 2, 1. This is 2, 3. 2, 3 is 5 minus 3 is 2. And then this one is 3 minus 2 is 1. Huh? I think that's okay.
1, 1.
So you're having, this is 2, this is 1, this is 1. Huh?
Now it's
Yes.
Good. Clearly, we all can see that these are positive values. Huh?
yes.
So when we see all of them positive, it means you have reached the optimum point. Huh? It means the value 565 is actually the optimal solution. We cannot spend anything less than that. That's the least amount we can spend to ferry all those goods from their sources to their destination. So that means you cannot reduce that total cost any further. So that's the comment or remark you make now after computing this optimal opportunity cost associated with that new figure. And so that is what will stop the iteration. That is why you now, your MODI method will stop. So that's basically MODI method, what you are doing. Remember testing there, if I may just pick up. Testing, first of all, that non-degenerate condition, which will always be almost true. And then you are now calculating the dual variables. And after getting the dual variables, you're now using them to calculate the opportunity cost. Now with the opportunity cost, you have said, if they're all positive, then that is optimal. You stop at that particular point. But if we get a negative, you go to that, the cell corresponding to that negative and draw a loop. Upon drawing the loop, you're just now assigning negative and positive signs alternatively, beginning with the first cell being positive. And then check now, among the cells with the negative sign, which one has the least amount? That amount is what you shift now to this new unallocated cell that you are actually investigating. And then you just adjust the transportation table accordingly, like that you have done. And the new table you get, you again now check whether it's optimal by the dual variables are testing for optimality, like what you have done. And so that is what is expected from us as far as MODI method is concerned.